So now we're going to talk about collision theory, which brings us down to the molecular level. And we're going to see what's happening with the molecules and how the rate of the reaction changes. So rate constants vary with temperature, which means that reactions are very temperature dependent, and we already saw that. We know that if we speed up the reaction, if we heat up the reaction should speed up. So the reason why that it's temperature dependent can be explained by collision theory. Okay, so collision theory assumes that for a reaction to occur, a few things have to happen. First of all, the molecules have to collide. They have to come in contact with each other. Otherwise, they can't react. Furthermore, they have to collide with the proper orientation, and they have to collide with enough energy to make the reaction happen. This minimum amount of energy required is called the activation energy and given the symbol E sub A, activation energy. All right, so what happens is that these molecules collide with each other and we have what's called a transition state. So we start out with the reactants, we end up with the products, but somewhere in the middle, something has to happen. There has to be a transition. And so this is what explains what happens during the collision. You actually have the collision of two molecules, and they create what's called an activated complex. And this is the transition state. It's an unstable grouping of atoms. They can break apart to form products. They can actually break apart to go back to the reactant. So they could go either way, but they're an unstable. It's not something you can isolate. While it's happening, it's very unstable and it's very, very quick usually. So these molecules come together, create this activated complex, and then they fall apart. Either fall apart and go back to what they were, or rearrange themselves and fall apart to give the products. So you can compare, a simple analogy would be the collision of three billiard balls. So let's look at the picture to the right, and let's assume that the two balls are coated with a slightly sticky adhesive. It kind of looks like they're really stuck together, but we're going to assume the red and yellow are kind of slightly attached to each other. And then we'll take a third ball, which is the white ball in this picture, and cover it with an extremely sticky adhesive and collide it with our joined pair. So at the instant of impact, when all three spheres are joined, we have what's called the transition state complex, which is unstable. You can't get it isolated. It doesn't last for very long, but it's called the transition state complex. And then generally what happens is the incoming white billiard ball sticks to one of the spheres, so let's say the red one. When it hits it, it provides enough energy to dislodge the yellow one, so the yellow one leaves, and now we have a new pairing. So if we repeated this scenario several times, many of the collisions would be successful, but others might not be, either because they don't have the right orientation or they don't have enough energy, etc. So we compare the energy needed to break those billiard balls apart, the activation energy. If we just very barely touch the white ball to the other, then likely nothing would happen. There wouldn't be enough activation energy. But if we do have enough activation energy, then the reaction will happen. Okay, so we can actually make a potential energy diagram, which takes time on the x-axis and energy on the y-axis, and we can plot it. We'll see the graph in just a second. We want to see that the activation energy is the energy needed to go from the start up to the activated complex, which we'll see in just a second. And the delta H of the reaction, the heat of the reaction, is just the change from reactants to products. So let's look at the Okay, so here you can see progress of the reaction, or time, on the x-axis, energy on the y-axis. And so we have the energy of the reactants is just a certain particular amount of energy. We have the energy of the products up on the top right. And then the path to get from reactants to products, at first we have to increase energy. Those reactants are coming closer and closer together. we get to the activated complex, which is the very top of the hump. The activation energy then is the amount of energy from the reactants up to the very top of the hump. That's the amount of activation energy. And then notice that as the activated complex breaks apart, the energy goes down a little bit because they're not so crowded in with each other, and so as they pull apart, energy comes down a little. In this case, the energy only comes down a little bit, and you can see the products are higher than the reactants. So this would be an endothermic reaction because overall energy had to be put in to go from reactants to products. The delta H, you can see the 83 kilojoules per mole is actually from the start, from the reactants, up to the products. And then they're also showing you some other numbers. The activation energy is 85 kilojoules, but then as you come back down the hump, you gain back 2 kilojoules. So overall, the energy needed to put into this reaction is 83 kilojoules per mole. So again, the main thing you want to know is to be able to pick apart the types of the parts of this graph, be able to identify the activation energy, the activated complex, which is sometimes also called the transition state, and you see that sort of double star looking thing next to the NOCl2, that means activated complex or transition state. Be able to determine the delta H for a reaction, be able to determine if this is endothermic or exothermic, which we'll see an example of in just a second. Notice that if you reverse this reaction, if you wanted to take NOCl plus Cl to give us NO plus Cl2, the activation energy is actually that little bit, that 2 kilojoules to get from the products up to the hump, and then you get a lot of energy back out the other side. So the reverse of one reaction is the other is the opposite. All right, so an exothermic reaction, as I said, shows that the products are lower in energy than the reactants. And so the next illustration will show an exothermic reaction. And again, the forward energy, if it's exothermic, the forward activation energy is always from the reactants up to the transition state complex. The graph. All right, so this is an exothermic graph. Again, we have our reactants, A plus B. The activation energy is from the energy of the reactants up to the activated complex, AB star star. So activation energy. Then in this case, because it's exothermic, the products are at a lower energy than the reactants. So in this case, delta H is negative because it's final minus initial would be a negative number. So the delta H is always from reactants to products. And then notice that if we did reverse the reaction, the activation energy would be from C plus T up to the activated complex, and then the activation energy of the forward is going from A to B, A plus B to the complex, and the activation in the reverse would be the opposite, just like we saw in the other. So obviously the opposite of it exothermic reaction is an endothermic reaction, and the opposite of an endothermic is an exothermic, and so the delta H just changes signs, but it stays the same value. All right, so look at these two graphs and tell me, are these reactions exothermic or endothermic? Okay, hopefully you can see that in both cases the products are lower than the reactants, and so they are both exothermic. Which reaction has a higher activation energy? Well, they both start at the same energy level and they both end at the same energy level, but the one on the right has a higher hump, which means it has a higher activation energy. It also means that in general it's going to be a slower reaction. Now, if both reactions were run at the same temperature and have the same orientation requirements, which one would have the larger rate constant? Well, that one's a little more complicated, but a larger rate constant would mean that the reaction goes faster. So which one of these, the reaction goes faster? The one on the left, because it has the lower hump. So it has larger rate constant, faster reaction, lower hump. All right, so what are 4 things that affect the rate of reaction? And we talked about these a little bit. The physical state of the reactants. First of all, they need to be able to come together. So the closer they are, the faster they react. If they're in different phases, the amount of contact between them is very important. So concentration, and we talked about this earlier too. The more molecules you have, the more collision. So we're looking sort of now at this at rate of reaction in terms of the collision theory and what's actually happening with the molecules. So concentration, again, the more molecules you have, the more collisions you have. A catalyst, generally what happens is it lowers the activation energy by giving the reaction a new path to follow, or it gives it a location for the molecules to come together, so it enhances collisions by giving it a location. And then finally, temperature. We know temperature increases the rate of reaction. Temperature does it in two different ways. So first of all, obviously, if molecules are moving faster, so if you increase the temperature, all the molecules start moving faster. So there's more collisions because they're all moving faster. So they're just more likely to run into each other. But also, you can see on this graph that the number of particles that have a lot of energy increases. So at T1, which is the lower temperature, let's say that blue line is sort of the activation energy, the amount required for the reaction to happen to get over the barrier. So at T1, you can see what's shaded in green is the number of molecules that have that much energy. So there's some. The reaction can proceed. But if you increase the temperature, you have more. Okay, so there are three things that will affect the rate of a reaction. So the constant, the K, the rate constant, is a product of these three factors. The collision frequency, so how often do molecules collide, the fraction that have enough energy to react, that have that activation energy, and then the fraction that have the proper orientation. So the rate law constant, K, is a product of Z times P times F. So it turns out that Z, how often they collide, is not as temperature dependent as you might think. So when we say that you increase the temperature and molecules collide more often, yes, that's true, but it's not the most important fact about the temperature increasing the rate. So what this slide is showing you, that velocity is directly related to the absolute temperature, but only the square root. Now, it also is related to molecular mass, but if you're talking about the same molecule, then everything is a constant, and we can say that velocity is directly related to the square root of the absolute temperature. So it's not as it doesn't affect the rate as much as you might. So in fact, if you have a 10-degree rise in temperature, it will only produce a 2% rise in collision frequency. So that's not the main reason that that temperature affects rate. Okay, so on the other hand, the fraction of molecules that have enough activation energy is very temperature dependent. You really don't need to worry about this equation so much, but basically this is the equation that shows the relationship between that fraction with enough activation energy equals e to the negative EA over RT. R is a constant, but basically because it's E raised to the negative EA over RT, if temperature increases, you're making that less negative, you're making that a smaller number and making it less negative, so F increases. Or also if EA gets smaller, because it's becoming less negative, F gets bigger. And so F is basically the number that, if the lower the activation energy, the more molecules, of course, that have enough activation energy. And as temperature increases, the more molecules that have that enough activation energy. And so that's the main reason why rates of reaction increase with temperature. So it's also dependent on P, the fraction of collisions with the proper orientation, but this is really independent of temperature. So the number of molecules that collide with the correct orientation has nothing to do with temperature. So so if temperature increases, Z and P are fairly constant, but it's the F, the number that have enough activation energy, that really makes the reaction go faster. So if we combine these terms, we can make what's called the Arrhenius equation. This is called the Arrhenius equation. It says that K, the rate constant, is equal to A, which is another constant, times E raised to the negative EA, activation energy, over RT. So this is called the Arrhenius equation, and it shows the dependence of the rate constant on the temperature and the activation energy. So you can actually do some calculations. You can find out what is the activation energy if you know A and you know the temperature and you know K. You can solve for different parts of this equation. If you take the natural logarithm of both sides, so you undo the E, you get this equation. The natural log of K equals the natural log of A minus EA over RT. This is, as we were talking earlier, you can plot this in a mathematical equation, rearranging them. So if you plot 1 over temperature times the natural log of K, so x versus y, then you can find that the slope is negative EA over r, and since r is a constant, you can find what the slope is just really going to be related to the activation energy, and then the intercept is the natural log of A. Again, we're not really going to focus too much on this. This is just kind of showing you ways that we can identify, we can find the activation energy, we can see how the rate law is related to temperature. So this is just showing an example of plotting the natural log of K on the y-axis versus 1 over T. And when you find the slope, the slope then is the negative activation energy over R. Again, I'm not going to ask you to do any of these types of questions. What this slide is showing you is that actually if you take that equation, the Arrhenius equation at 1 temperature, and so they're calling that natural log K1, what's the rate law at a certain temperature at T1, and then rewriting the same equation at T2, giving us a new rate law constant, K2. And then if we combine these equations together, which that is not something you need to do. We're just using the result of it. So if we eliminate A, which is something maybe would be hard to find, we can come up with this equation. The natural log of the ratio of K2 to K1 equals EA over R, 1 over T1 minus 1 over T2. So basically what this equation says, if you know the two temperatures and you know the rate constant, either the rate constant at both temperatures, you can find the activation energy, or if you know the activation energy and the rate constant at one temperature, you can find the rate constant at another temperature. And the next problem shows the example. So this is just an example of using that previous equation. Say the rate constant of formation for this reaction is 2.7 times 10 to the minus fourth at 600 K, and then at 650 K it raises up to 3.5 times 10 to the minus third inverse molarity per second, and they want you to find the activation energy. So basically you're just plugging in everything you know. So you have the natural log of K2 over K1 equals the activation energy over R. R, and this time we're using the constant 8.31 in terms of joules per mole Kelvin rather than the gas law constant 0.0821 liters atmospheres, because we want to know joules energy. So this is just the other term that we use if we want to know joules. And then we have the T1 minus T2. And so if you take the natural log of that ratio, it equals 1.11, and then multiply by the 8.31, divide by the 1.28 times 10 to the minus fourth, and we'll find the activation energy is 1.66 times 10 to the fifth. Again, I'm not super interested in doing the Arrhenius equation. It's just a way of being able to determine the activation energy, and it's really just a matter of plugging in the correct values, but it can be very useful.